Yeah, very good morning. Am I audible? Am I audible?
Yes.
Yes, sir, you are audible.
Okay, thank you. Yeah, so screen is visible.
Yes, sir.
Yes, sir.
Yeah, so we have done some first order PDs, and we have seen some of the special type of PDs, first order, how to solve them by using method of characteristic or same method of Lagrange. And also we have seen some special type of nonlinear first order PDs. Now, the next we are going to move towards solving a second order PD. But before going there, we need to have understanding of some of the important concepts known as Fourier series, Fourier transform, okay, or Fourier integral, Fourier sine transform, Fourier cosine transform, okay, so that the solution is easily approachable. Okay, so it is necessary to introduce first the concept of Fourier series, then we will move towards Fourier integral, and then we will end up with Fourier transform, and then we will apply this knowledge to solve some special type of second order PDs, and see what will happen then. Okay, and we'll see some of the application part as well. Right. Okay. So Fourier series is a concept which will actually represent a function which has some additional properties, like function is periodic. Okay, means after some period it will occur, it will again uh, uh, it will again go through with the same trajectory, you can say. Okay, so like a cosine curve, sine curves, you have seen they are periodic function of with period 2 pi. And how would you decide the period is also is the smallest length, okay, among, means like you have 0 to 2 pi, okay, then 2 pi to 4 pi. So you may also say, sir, 4 after 4 pi, so 0 to 4 pi, 4 pi to 8 pi, you are getting the same thing. Okay, that also you will say that also could be the possible period. Again, 0 to 6 pi, 6 pi to 12 pi, and so on. Okay, so they can also be treated as a period, but not. But definition says that the smallest length. Okay, so the smallest length is 0 to 2 pi. Okay, so it a Fourier series essentially represent is some special type of function which has some not a big not a very strong assumptions required on that, okay, except the periodicity. Okay, so that you can actually represent in the in terms of cosine, in terms of cosine function and or sine function, or summation of cosine function, sine function, either in finite number of terms or it may be infinite number of terms. So series itself represent means you are going to work towards an infinite series somehow. Okay, but again, as an engineer, you want to give means your input in your computer you will program it. Okay, so then in the program, infinity is no such kind of concept. So definitely you have to work with the, instead of infinity, number of terms you are going to include. Okay, max, so that you can increase n to, let's say, 2n, then 3n, and so on, and then you can also see the behavior, okay, there, and whether it will converge to the actual curve or not. That also, it's a very interesting application. You can take it if you know some of the certain language, such as like MATLAB or somewhere. You can we have also started, if you have started working on Python, okay, then it will be easy for you to look at such type of graphs. Okay, or else if some time allows, I will give some graph. Okay, here also we have some graphs here. Okay, later stage. Okay, so let's move forward. So it's named after this Joseph Fourier. Okay. So he has actually worked on this problem of heat distribution in a metal plate. Okay, and there he has looked at some periodicity and he has driven some concept. That time it was not acceptable by many mathematicians, but later on it has been acceptable, and with a proof, a mathematical base. Okay. Right. Okay. So let's so as told, this Fourier series entirely works on the a class of functions which are periodic. So first of all, you have to verify that whether the function has a periodic behavior or not. How to decide? Here is the definition. Okay, mathematical definition. A function f is said to be periodic with period to t. So capital T is denoted as a period, and of course t being a non-zero constant, t should not be zero. If we have the following for all x, okay, so that will give you the definition of a period. So it's said to be periodic with period t if we have this. So of course we have the t is the smallest one. Okay, that will say as a period. So if there exists a least positive constant, that support my statement that if they that you are going to choose a smallest one, okay, optimal one. So if there exists a least positive constant t, cos period is always a positive one. With this property, it is called the fundamental period. That also can be named, okay, in this fashion as well, fundamental period, also known as primitive period, basic period, or prime period. So there are several synonyms towards this. Okay, so whenever you say f is a periodic function with period 2, with period 2 t, and so on, means we are having the understanding that it's a least positive constant with this property. Okay, right. So means here is so what is the nice thing attached with this class is sum of two periodic functions with the same period will be also periodic with the same period. Okay, so this note will say that f and g, suppose two functions with period p, they are sharing the same period. Please note that. Okay, that their linear combination af plus bg with any constants a and b. So a and b are any arbitrary constants, real numbers. Okay, so far we are only introduced with real numbers. With any constant a and b, then also it also has the PFP. So that can be easily verified. Okay, so it is like AF plus BG. You know how to perform this x plus p, suppose p the period. You know how to write this. So this is going to be AF of x plus p plus BG of x plus b. Now this is equals to a time f of x plus b. You have to follow these definitions, how to perform the sum of two functions and scalar multiple of two functions. Now use the fact that f is and g are periodic with period p. So this is equal a f of x plus b times g of x, and that you can certainly again rewrite it as af plus bg of x. So this small evaluation shows that af plus bg also has the same period. Okay, so right. So there are some of the functions. So the very first function you can look at is sine and cosine waves. So here red ones are the sine curves and green one are the cosine curves. Okay, so it is very easy to verify, okay, that they are going to be periodic with period 2 pi. So you have this is minus pi to plus pi. Okay, this is minus pi to plus pi. You can take this interval, okay, which for which this is a periodic with period length is 2 pi. Okay, right. Similarly for cos curve as well, we have this minus pi to plus pi. Okay, so this is a periodic curve. Okay, these are the periodic functions with period 2 pi. Okay, so that is also easy to verify that sine of x plus 2 pi is sine x, cos of x plus 2 pi is also cos x. Okay, because they are lies in the fourth quadrant, and sorry, not fourth quadrant, first quadrant, 2 pi plus theta. Okay, you can use that fact trigonometrical. Okay, right. Now another nice example is sawtooth waves. Okay, so you can take this again minus pi to plus pi. Okay, so over this interval minus pi to pi, so you have so you have to have this is going to be this one, right? Okay, so over this interval minus pi to pi, instead of this you have this is going to be this one. So this is the line, straight line. Okay, if you want to represent this curve, what it will be? Yes, if mathematically, if you want to represent this curve over the, let's say over the interval minus pi to pi. So s of x is equals to so you have this is going to be, this is the point is minus pi comma minus 1, right? And this is the point pi comma 1. So you have 2 points. You can find the equation of the straight line passing through this, right? Passing through origin. Yes. X by pi, right? S of x equals to x by pi. X is minus pi less than x less than pi, right? Or less than equals to, right? So this is right at x equals to minus pi, s of x is minus 1. At x equals to pi, s of x is 1. We have this straight line. right? So here you may see here at the end points, there may be a discontinuity, there may not be. They will also, we will also look at them. Okay, so it depends again whether we can include this also in the Fourier series concept or not. That is answered by Dirichlet. Okay, that's known as Dirichlet condition that we will soon look at. Okay, right. So now there are another curve are known as square waves. Okay, so square waves also you can have from minus pi to pi. You can have this curve, and again you can represent these curves, okay, by a mathematical definition as well. Okay, so between minus pi to 0, the value is 1. Between 0 to pi, value is 1. So here is minus 1 and here is 1. Okay, right? So your goal is something else, okay, in the Fourier series, means you are going to represent. So see, these are the periodic waves, so square waves, sawtooth waves. So here is the sine and cosine waves. So Fourier, what he has tried is he has tried to approximate these sawtooth waves or square waves or any other waves, rectangular waves, okay, or some other type of waves, okay, by using the linear combination of this following set. Okay, so you can look at the behavior of them as well. So cos x, you know, between 0 to 2 pi, you have the following. So if you, instead of cos x, you have cos 2x, you have 2 time oscillation, right? If you have cos 3x, you have 3 time oscillation. Similarly for sine curve. Okay. Now, moreover, you can also look at here what we are also going to give in the Dirichlet conditions as well. Another important thing is between this period 0 to 2 pi. Okay, if you increase the number of oscillations, no, sorry, if you increase the here means x coefficient is 2, 3, and so on, the number of oscillations are becoming more and more. But as long as finite, so how many number of extrema? So in the first case, it is 1, right? Only this. Here is 1, 2, 3. Here is 1, 2, 3, 4, 5, and so on. Extrema, you know, maxima or minima. Okay. Similarly for this, okay. Similarly, they are finitely many. Okay. So that also is that also will be included in the Dirichlet conditions, so that you will soon see those conditions. Okay, right. So the question is now, as I told you, he worked on the linear combination. So Fourier worked on the linear combination of the previous set. So you can multiply, this is A naught, okay, A naught multiplied by A naught, cosine will multiplied by A1, A2, A3, and so on, AN. Sine will be another constant like B1, B2, Bn. Okay, and take the linear combination. So, as we know already, if you have a finite sum, there is no problem in writing this summation n equals to 1 to, let's say, capital M. It's not a problem. But when you replace this M by infinity, always there is a problem. Okay, you have to verify whether this infinite series converges or not. Okay, so you have those concept in function of single variable, we have seen, okay, those type of thing, infinite series, okay, then a ratio test, okay, and so on, whether this infinite series converges or not. So that concept, so if this series converges, this equality is perfectly fine. Otherwise, no. Okay, right. Now, okay, so it will be fine when the infinite series on the left hand side converges. So here are the discrete conditions. So f must be absolutely integrable over a period. You have heard Riemann integrable, right? You have not heard so far absolutely integrable. So what is that mean is, suppose you have the period is, let's say, over a period means over this interval, let's say minus L to capital L. F is defined on this domain. Okay. So what does it mean is integration minus L to capital L absolutely means mod of f of x dx is finite. This is the meaning of absolutely integrable over that domain. Is that clear? Absolutely integrable. Integrable means you have f of x without magnitude. Okay, that is less than infinity. Means converges type of, it may be an improper integral. Okay, but improper, but that may converge or diverge. So if it diverges absolutely, okay, then this discrete condition will not be satisfied. So it should be converges absolutely. So absolute integrable means this integral should be finite value, should have finite value. Okay. Another discrete condition is it is allowed to have finite number of extrema. Okay. Means you have over a period 0 to 2 or minus L to L. Okay. So you have finite number of oscillation. Okay. Not an infinite one, means you don't have like this. Okay, though it is countable, but is it countably infinite? Okay, though it is countable means you can still move on. This is first, second, third, fourth, fifth, sixth, seven, eight, nine, 10. If they are getting closer and closer and closer, well, it is still countable. One can sit and count, keep on counting, but that counting will never end. Okay, so that we will say in that sense is countably infinite. Okay, so it has finite number of extrema in any given bounded interval. Okay, now the next is only finitely many point of discontinuities. Okay, so for that we have seen like sawtooth waves, or you have this square waves. Okay, so you have square waves, you have this is so you have square waves. And so on. So means you have, let's say this is here is 1, here is minus 1. Okay, so that will identify a square wave. Okay, so you may also include this line and this line, but here at the point discontinuity. So finitely many discontinuity points are allowed, not infinitely many. Okay, in other words, f must be piecewise continuous over that bounded interval. Okay, so with these discrete conditions, so we have now final result. Okay, that f can be represented as a in terms of that infinite series. Okay, now then we will try to answer the question whether I can, for every value of x, f of x is equals to this or not. That we will try to answer. Okay, so here is the statement. So it's very clear now. So it is a Fourier series on minus pi to pi. Okay, so we can extend this concept over the interval minus capital L to plus capital L. Okay, that will be easy. That we will work on. Okay, little later. Okay, so let's say f of x be periodic with period 2 pi. So instead of 2L, you have 2 pi. and it is piecewise continuous in the interval minus pi to pi. Okay, so it says that you are allowed with only finite number of discontinuities. Further, let f of x have a left-hand derivative and right-hand derivative at each point of that interval. So what is this understanding is f may or may not be differentiable over the interval, but at every point of the interval, it has left-hand derivative and right-hand derivative. So if left-hand derivative and right-hand derivative are equal, then it is a differentiable. Otherwise, not differentiable, right? So let f and f has left-hand derivative and right-hand derivative at each point of that interval. Then the function, so these conditions need to be verified. Okay, then the function f of x can be represented as the infinite series, the following. Okay, a naught, a n, bn. So what you need to determine a naught, a n, and bn. Okay, they are known as Euler formulas. I mean, they are given by the formulas which are known as Euler formulas, and which is very easy to derive as well. Okay, so a naught plus summation n equals to 1 to infinity a n cos nx plus b n sin nx, which converges with the coefficients given by the Euler formula that are known as Eulers. Okay, so here are the formulas. Okay, how they have arrived, I will discuss after this completing this result. So its sum is f of x. So this will answer your this question that whether f of x equals to this or not. Okay, so this answers this one. So its sum is f of x except at point x naught, where f of x is discontinuous. So what it says, at the point of continuity, suppose function is continuous at a point x naught, then you can write that f of x naught equals to f of x naught equals to a naught plus summation n equals to 1 to infinity a n time cos of n time x naught plus b n times sine of n time x naught. Okay, at the point of continuity. On the other hand, if function is discontinuous, okay, means function is not continuous. So you have left hand limit and right hand limit. Okay, so in that case, then the later case, the sum of the series is nothing but the average of them, average of the left hand and right hand limit of f of x at x naught. So in the case of discontinuity, at a point of discontinuity, the series is equals to f of x naught plus f of x naught minus divide by 2. So average of them. Okay, right. So now we are going to work on how to derive this Euler formula. Okay. Okay. Now see. Let's try derivation. So suppose f is continuous at every point of that interval, so that the things will be nice, and you have f of x is equals to a naught plus summation n equals to 1 to infinity a n time cos nx plus b n time sin nx. Okay, now perform the integration. Now integration minus pi to pi f of x dx is equals to perform integral. So what we are assuming that the things are nice. Again, the things are nice means infinite series is convergent. Moreover, what we are also assuming that they are interchangeable, means you can take inside integration. Okay, so these two things we are assuming here. So this is not simply allowed. Okay, so integration minus pi to pi a naught dx plus this integration I am taking inside, means we have the assumption, okay, n equals to 1 to infinity a n time integration minus pi to pi cos nx dx plus bn integration minus pi to pi sine of nx dx. Now, you can easily verify that this integral value and this integral value will be 0. Okay? That I left to you. Cosine integration, you know, sine. Sine integration, you know, cos. Okay? So that's very easy to verify that output upper limit minus lower limit, that is 0 for each value of n. So the left and right hand side is equals to, so a naught is interval integration minus pi to pi dx is nothing but the length of the interval, that is 2 pi a naught. Okay, that you can verify that this integral will be 0. The second integral also will be 0. So this will imply a naught equals to 1 upon 2 pi integration minus pi to pi f of x dx. So this is first, that Euler coefficient. Now to determine an, what we will do is we will multiply both sides by cos mx. So this we can call as this equation number 2. Sorry, not 2. Let's say 1, and that's, let's say, 2. Okay, so multiplying 1 by cos mx. So instead of n, we have choose m, that is fixed. Okay, that we will choose accordingly. Okay, how it will help you is as follows. So multiply both sides of 1 by this. So you have an integrate over minus pi to pi. So what we will get is integration minus pi to pi f of x times cos mx dx is equals to e naught time integration minus pi to pi cos mx dx, okay, plus summation n equals to 1 to infinity an time integration minus pi to pi cos nx time cos of mx dx plus bn time integration minus pi to pi sine of nx time cos of mx dx. Okay, now the first term, the right hand side, a naught time integration minus pi to pi cos mx dx. It's easy to verify that this term will be 0. Sine mx by m, you know, sine m is m by cos mx and integrate this. So m is any natural number. Okay, m is any natural number. So cos, sine pi, sine 2 pi, sine 3 pi, sine n pi is 0. Okay, so this first term will not contribute anything. Now, second term, we will come. Third term here. Now you will see the sine a cos b. Okay, so you can use this sine a cos b formula to integrate it. Okay, and verify that this is going to be 0 for each value of n and m. Okay, so this is I think I can left it as an exercise for you. This is very easy because you know how to solve. You multiply 2 to divide by 2. Similarly, you divide by 2, multiply by 2, and use the 2 cos a cos b and 2 sin a sin b formula. Sin a sin b is 2 sin a cos b formula. Okay, so this term, the third term, will also not contribute anything. Okay, so I'm going to write now only the second term, summation n equals to 1 to infinity an pi 2 integration minus pi to pi. Now 2 cos A cos B is, cos of, yes, cos of 2 cos A cos B. So cos of A minus B, right? Plus cos of A plus B, right? Cos of n minus m x plus cos of uh, m plus n dx. Okay. Now, see, everything is fine. Okay. Everything is fine means like whenever m is not equals to n. Okay. Because if m is equals to n, this becomes 0. Cos 0 is 1 and this will lead to non-zero point. Non-zero number 2 pi. Okay. So whenever n is not equals to m, whether n is greater than m or less than m, okay, either of the term. So in that case, you can also still verify that both these terms will not contribute anything. Okay. So this will only contribute and as long as m is equals to n, only first term. Second term, no longer. Okay, doesn't matter whether m is equals to n or m is not equals to. Okay, so this is equals to a m by 2, so n equals to m. Okay, integration minus pi to pi dx. So this is equals to pi time am. Now, what was the left hand side? Was integration minus pi to pi f of x time cos mx dx is equals to pi time am. So this implies am is equals to 1 by pi time integration minus pi to pi f of x time cos of mx dx. So this is, let's denote it by 3. Now, similarly for B. So you instead of now this is true for, means we have started for fixed m. Now you can vary this m. Okay, m equals to 1, you can find out a1 equals to. M equals to 2, similarly you can find a2 equals to, and so on. Instead of m, you can use this n index as well. Okay, so now to get the last Euler coefficient, that is Bn, what you will do? You will multiply both sides by sine mx. Okay, and then again integrate over the interval minus pi to pi. Okay, and that will lead to that formula that Bn equals to 1 by pi integration minus pi to pi f of x sine nx dx. Okay, so this also I can leave now as an exercise for you. Okay, so I've given you the way to derive this. So if you're interested, you can verify that. Moreover, sometimes what will happen in most of the textbook, it may also have, they may also, instead of this, they may write a naught by 2 plus something. Okay, why it is so? So that this 2 will be removed and you can, instead of this an equals to, you can, n is here is n is equals to 1, 2, 3, 4 and so on. You can start here n equals to 0. Okay, so there is no, there are various ways to represent it. Okay, so many times you will have textbook a naught by 2, sometimes you have a naught. So if you have a naught only, so you have the following formula. If you have a naught by 2, then you have here 1 by pi integration minus pi 2. Okay, so keep in that mind. Okay, about this. Okay, right. Now let's I think I have some problems now. Yes. So find the Fourier coefficients of the periodic function f of x in the figure below. So these are the square waves. Okay. So minus pi to 0, the value is minus k. Okay. And between 0 to pi, the value is k. Okay. So this is the definition of this. Okay. Okay. So you have f of x is equals to minus k if minus pi less than equals to x less than 0, k if 0 less than equals to x less than pi. Okay, so various ways to define this. Okay, so you have at minus pi, you have a minus k. Yeah. This is 3 pi here. Okay, so pi to 2 pi minus k, and you have 2 pi to 3 pi plus. Okay, so instead of this, you can also, whether if you want, you can include this point or not. That also doesn't matter because finitely many point of discontinuities are allowed. Okay, right. So okay, right. So now we are interested in finding those Euler coefficients. So first we have to verify that is verify that the conditions known as Dirichlet conditions. So first thing is integration minus pi to pi mod of f of x dx. So this has finitely many point of discontinuity. It is a Riemann integrable function. Okay, there is no point of no doubt about it. So this is integration minus pi to 0 plus integration 0 to pi and mod of f of x minus pi to 0 or 0 to pi. Both are k. Okay, so it is easy to verify. Okay, so it is k time pi here plus k time pi. That's going to be 2k pi. 2k pi, which is finite. It's absolutely integrable, piecewise continuous. Okay, piecewise continuous. It is at the end point and at the midpoint 0. Okay, piecewise continuous. They are not point of continuity. But okay, now another thing is it has only finite number of extrema, right? Over this interval, only 2 time, right? 1, 2. Okay, right. And between this minus pi to 0 and 0 to pi, over this open interval, it is differentiable because it's a constant function. At the end point, it has left hand derivative and right hand derivative. Those all our conditions can be verified. Okay. Moreover, by the graphical representation, okay, it is very clear that f of x plus 2 pi is equals to f of x for all x. So it is of periodic with period 2 pi. So all the Dirichlet condition is satisfied. Now, we are supposed to identify now those Euler coefficients. Euler, right? So what is A naught is 1 upon 2 pi integration minus pi to pi f of x dx. So right now we are working over the interval minus pi to pi. We may also work on 0 to 2 pi and so on, that we will see later on. Okay, so minus pi to pi. So this is equals to 1 upon 2 pi integration minus pi to 0 minus k dx plus integration 0 to pi k dx. So you know this is going to be minus k pi plus k pi. That's going to be 0. Okay. Now an is equals to 1 upon pi integration minus pi to pi. Okay. F of x time cos of nx dx. So that is equals to 1 upon pi integration minus pi to 0 minus k cos nx dx plus 1 upon pi integration 0 to pi k time cos of nx dx. Now this is equals to 1 upon pi minus k sine of nx divided by n minus pi upper limit 0 lower limit minus pi plus k by pi sine of nx divided by n lower limit 0 upper limit pi, and you know sine 0 0 sine of minus n pi is also 0, so these four contribute will turn out to be 0. Now let's find out the bn. 1 upon pi integration minus pi to pi f of x time sine of nx dx. So that's equals to minus k by pi integration minus pi to 0 sine of nx dx plus k by pi integration 0 to pi sine of nx dx. I'm using the definition f of x is minus k over minus pi to 0 and is plus k from 0 to pi, and they are taken out. Now sine integration is minus cos k by n pi, so minus minus plus cos of nx minus pi to 0 plus k by n pi with minus sign, right? Cos of nx 0 to pi. Now this is equals to k by n pi. You know cos 0 is 1. Okay, cos 0 is 1 minus cos of n pi. Okay, minus k upon n pi time cos of n pi minus cos 0 is 1. Okay, now what is it further? That is equals to 2k by n pi 1 minus cos of n, right? Because if you take here minus inside, it is going to be 1 minus cos n pi, and you have 2 times this. Okay, so now what is cos n pi is going to be 1 minus 1 to the power n. So if n is even, this term will be 0. So everything will be n is 0. So that's equals to 0 if n is even number. And if n is odd, you have this is 1 plus 1 is 2, 2 times this 4 pi by 1. This is 4. Two k, right? 4k by n pi. So finally, you have f of x can be represented as a naught by 2 plus summation n equals to 1 to infinity an time cos of nx plus bn times sine of nx. Now a naught is 0, an is 0, so this equals to only sine series. So what we have got is sine series. Okay. Now this is equals to 4k by pi, because Bn is 0 for even case. Okay. For OR case, so OR is means n equals to 1, n equals to 3, n equals to 5, and so on. So sine x plus sine 3x by 3 plus sine 5x by 5 plus and so on. So this is the following is the Fourier series representation for f of x. So if you want to write f of x, this, and you can write this symbol here approximately equals to this. Okay, Fourier series. Now, so we have the following. So this is we have obtained. Now you can take first term only for graphical. You can include second term, then you can include third term, and then you try to get the different plots. Okay, so let's call this S1 is a 4k by pi sine x. S2 is the second, which includes the second term. Okay, and S3 is the third, which includes the third term. Okay, and then if you use the MATLAB, okay, so you have the following S1 is this. Okay, this is the S1. Okay, and this is the original. Okay, right. Now, if you use S2, S1 is there. Okay, this dot. Okay, now if you use S2, this is the S2. Okay, which is obtained by using MATLAB again. Okay, so S2 is more closer, so you can see that there are more number of oscillations along this line. Okay, similarly here, if you increase more, S3, this is the S3, so you will see here more number of oscillations. So if you keep on improving, it will be like, okay, it will be like this. Okay, it will be like here, approximating this. Okay, so this is the beauty of Fourier series. Okay, right. So if you have any doubt, you can ask. Time is there. So if you have any doubt, you can ask. Yes. Okay. So these integral values you can verify. Okay, them. Okay, you have to just use this again: 2 cos A cos B, 2 sin A sin B, and 2 cos A sin B formula, and use this. And this is a direct delta function. Delta Mn is equals to 1 if m is equals to n, and is 0 if m is not equals to n. So this is how it is defined. Okay, so that you can verify. Okay, multiply and divide by 2. Use that formula. Okay, right. So now, if you wish to move, instead of interval minus pi to pi, suppose you have the interval minus 1 to 1, how to move? Okay, so that's a very interesting. You can look at here some little tricky thing: minus pi less than equals to x less than equals to pi. The domain is this. what you can do is you can divide, because pi is a non-zero quantity, so this will imply -1 less than equals to x by pi less than equals to 1. What you want is over the interval minus L to L. So this will give you multiply, because L is a non-zero quantity again. Okay, non-zero and positive quantity because it's a period, right? 2L. So minus L less than equals to XL by pi less than equals to capital L. Right? So this will tell you whenever x is lies between minus pi to pi, XL by pi will lies between minus L to L. Okay. Now, or in the reverse manner, you have this is minus L less than equals to x less than equals to capital L. You can have -1 less than equals to x by L less than equals to 1. Because you know the series over minus pi to pi, you have to go in the reverse direction. So this will implies minus pi less than equals to pi x by L less than equal to capital pi. So instead of x, you can use pi x by L over the interval minus pi to pi. Okay, so wherever you have seen x in the previous series for over the interval minus pi to pi, you can replace x by pi x by L. That will give you that, because x, whenever x lies between minus L to L, pi x by L lies between minus pi to pi, you can obtain the Fourier series for this easily. Okay, so you have to just change the other notations. Okay, so here is the final observation. Now the Fourier series of f on the interval minus L to L is, this is right, cos of nx. It was there, cos of nx and sine of nx. Okay, so x is replaced by pi x by L. So n time pi x by L. Okay, similarly here also nx is replaced by n pi x by L. Accordingly, you have to also replace in the formula. So L is replaced by L is replaced by pi. Okay, and x is replaced by here whenever it is sitting with here. Okay, argument of the cosine and sine, not inside the f. Okay, so sine of n pi x by L, cos of n pi x by L. So these are the only notation will be changing. Okay, or else you have the following representation. Again, you multiply both sides by sine of n pi x by L and integrate over the interval minus L to L. You will obtain the Bn. If you multiply both sides by cos of n pi x by L and integrate over the interval minus L to L, you will get An. Okay, and if you integrate both sides over minus L to L, you will integrate A0. Okay, so the method will be same. Okay, to obtain this Euler coefficients. Okay, right? Now, so this is one example of a periodic rectangular wave. Okay, so which is k between -1 to 1, and which is 0 between 1 to 3. Okay, right? Yeah. So this is the you can observe from here f of x equals to, okay, k if -1 less than equals to x less than equals to 1, and 0 if 1 less than equals to x, 1 less than x less than equals to 3. Okay, so you have the interval is -1 to 3. Okay, -1 to 3. Okay, -1 to 3. So 2L is equals to length of the interval, right? 3 minus minus 1, that is 4. So from here, L equals to 2. Okay. Now, okay, it's because so far we have not done for this any arbitrary interval. Okay, so we are working only over minus L to L. So let's keep it with this. Instead of this, we can use the following. Okay, because as per requirement, we are not defining in this way. We are defining in another way, is between minus 2 to 2. Okay, so minus 2, 2 plus 2. So you have, this is minus 2, 2 plus 2. So that between minus L2 plus L. Okay, so minus 2 to minus 1, it is 0. If minus 2 less than equals to x less than equals to minus 1. K if minus 1 less than x less than 1. 0 if 1 less than equals to x less than equals to 2. Okay, so the interval is minus 2 to 2. L is equals to 2, right? Now you have everything, every information. So it's a periodic. We can verify that those conditions periodic. It is a piecewise continuous, has finitely many point of extremum points. Also between every interval inside every upper interval, it is differentiable. Okay, and at the end point, it has left hand derivative and right hand derivative and so on. Okay, so those all conditions are here true. So it has the Fourier series representation. Now, A naught, you can find easily 1 by 2L integration minus L to L f of x dx. So here L is 2. So that's equals to 1 by 4 integration minus 2 to plus 2 f of x dx. So it's going to be 1 by 4 integration minus 1 to 1 k time dx. So it is going to be is equals to 1 by 4 time k 2k, right? Yes. So this is going to be k by 2. So A naught is equals to k by 2. Similarly, An is equals to 1 upon L, that is 2, integration minus 2 to 2 f of x time cos of n pi x by L, L is 2. Okay, so that's equals to 1 by 2 integration minus 1 to 1 k time cos of n pi x by 2 dx. Now, note that this over this interval means okay, you can integrate it. So this is equals to 1 by 2, so k by 2. Cos integration is sine of n pi x by 2 divided by n pi by 2 minus 1 to plus 1. Okay. So these 2 will get cancelled, k by n pi. So sine of n pi by 2 minus sine of minus n pi by 2. So that is minus minus plus, sine of minus theta is sine theta minus sine theta. So you have 2k by n pi sine of n pi by 2. Sine of even multiple of pi by 2 is not even. Okay. So if n is even number, it is 0. If n is odd, it is a either 1 or minus 1. Okay, so you have to handle it accordingly. Similarly, Bn is equals to 1 upon 2 integration minus 2 to 2 f of x time sine of n pi x by L, that is 2 dx. So this is equals to 1 by 2 integration minus 1 to 1 k times sine of n pi x by 2 dx. Now this is equals to k by 2. Now sine integration is minus cos n pi x by 2 divided by n pi by 2, upper limit and lower limit minus 1 to 1, but that is going to be 0. This is going to be 0. Okay, cos n pi by 2 minus cos of minus n pi by 2, because you know cos of minus theta is cos theta. Okay, right? So Bn is 0. So finally, your series is k by 2 here. So you will only obtain the cosine series. Okay, because you are only obtaining this an coefficients only if you have n is even, it is a 0 number. So for n is odd only, it's alternate plus minus you will have. So this is why here cos of pi x by 2, cos of 3 pi x by 2, 2 is missing. Similarly, cos 5 pi x by 2 and so on. And you will have alternate plus minus here. Okay. And now with this series, you can actually, now there are various open software available where you can actually put this and you can get their plot. Okay, so keep plotting additionally 1 term, 2 term, 3 term, 4 term by using those softwares, okay, online, and try to see whether it is if you include more and more, whether it is going towards this rectangular wave or not. Okay, right. I think we can close here. If you have any question, you can ask. Okay, then. Thank you.
Yes, sir.